Swayam Prabha. Digital India. Educated India.
Introduction to Global Positioning System. Global Positioning System, that is GPS, is a technology which provides unequaled accuracy and flexibility of positioning for navigation, surveying and GPS data capture. The GPS Navstar, that is navigation, satellite, timing and ranging, is a satellite based navigation, timing and positioning system. GPS provides 3D continuous positioning 24 hours a day throughout the world. The technology is beneficiary to GPS users in terms of obtaining accurate data up to about 100 meters for navigation, meter level for mapping and down to millimeter level for geodetic positioning. The GPS technology has tremendous amount of application in GPS data collection, surveying and mapping. The basis of GPS is on the geopositioning of the instrument where the GPS is placed. So, let us discuss the basic concepts related to geopositioning. First of all, positioning relates to the determination of positioning of stationary or moving objects. Well, this can be determined by either defining the point in relation to a well defined coordinate system, usually by 3 coordinate values, or in relation to another point, taking one point as the origin of a local coordinate system. In the first mode of positioning, known as the point positioning, while the second mode is known as the relative positioning. If the object is positioned is stationary, it is known as static positioning. When the object is moving, then it is known as kinematic positioning. Usually, the static positioning is used in surveying, while kinematic positioning is used for navigation purposes. With this, let us look at some of the GPS components and the basic facts which are involved in GPS technology. The GPS uses satellites and computers to compute position anywhere on the earth and is based on satellite ranging. This means that the position of the earth is determined by measuring the distance from a group of satellites in space. The basic principle behind GPS is really simple, even though the system employs some of the most high technology based equipments ever developed. In order to understand GPS basics, the system can be categorized into 5 logical steps. This slide shows the 5 logical steps which are there. First of all, we find the distance from the satellites which are used. In order to find out the distance, we need to find what is the time required by the signal to travel from the satellite to the point on the earth. Thus, the second step is we require accurate clocks. Having determined what is the time, then we also need to know what is the precise position of the satellites. So, the third step is to need to know the satellite location. Since the signals are traveling from the satellite to the earth and in between the earth's atmosphere is encountered by the signals, thus we need to undertake certain procedures to correct for atmosphere and ionospheric effects which may deteriorate the signal characteristics. Finally, the fifth step, which is selective availability. However, at present this particular step is eliminated and hence may not be considered in the actual process. So, let us look at the first step. The first step, our emphasis is to compute a position in 3 dimensions, for which a minimum of 4 satellites have to be observed. This particular slide shows 4 satellites which have been tracked by the GPS receiver, and on the basis of this it is now going to compute its own location on the earth surface. The second step is to triangulate the GPS measures the distance between the travel time of the radio message which has been received from the satellite, and second is to measure this travel time. It requires a very accurate clock. In order to do so, it basically tries to look at the codes which have been received from the satellite and what has been the time difference between the same part of the code. The same has been illustrated at the bottom part of the slide, wherein one can see the signal pattern as it has been received from the satellite and the signal pattern as it has been received at the ground level. Based on this, the distance between the between the 4 satellites will be determined to triangulate the GPS position. The third step is that once the distance of the satellite is known, then the location of the satellite in space is required. This information is provided by the master control station, which provides accurate information regarding the position of the satellite at the time of observation. Here we can see that from the master control station, the satellite is receiving its exact position, and based on this it is transmitting the same to the user, so that the exact position of the satellites are known and can be used for subsequent computations. The fourth step is basically to provide a correction to the signal transmission which has taken place. This is primarily because of the atmosphere layer which occurs through which these signals have to travel. So, we have to work out what is the delay which has been imposed by the atmosphere onto the signal which has been transmitted by the satellite and has been received by the GPS receiver. Having had a look at the logical steps which are involved, now let us look at what are the main components of a GPS. The GPS is divided into 3 major components, that is the space segment, the control segment and the user segment. So, let us look at each of these segments, the layout in totality. This particular slide shows us all the 3 components which are involved in the GPS activity. The space segment consists of these GPS satellites. The control segment is the one which controls the movement of the satellite and provides all the information to the navigation purposes of the satellite and its orbital characteristic. And the third segment is the user segment, wherein the GPS antenna has been placed on the earth surface, and this is the point for which the coordinates have to be computed. So, let us look at them one by one. The first segment is the control segment. The control segment consists of 5 monitoring stations, that is Colorado Springs, Ascension Islands, Dio Garcia, Hawaii and Kwajalein Island. This particular slide shows the location of all the control stations which are there. It may be interesting to note that apart from Colorado Springs, all other control stations are located around the equatorial region, because these satellites are revolving continuously around the earth's surface in such a manner that they need to be controlled as they are passing through the equatorial plane. By and large, it has been found that the Ascension, Dio Garcia and Kwajalein control stations serve as uplink installations capable of transmitting data to the satellites, including new ephemeris, that is satellite position as a function of time, clock, corrections and other broadcast message data. Colorado Springs serves as the master control station. The control segment is a total responsibility of the Department of Defense, US government, who undertakes the construction, launching, maintenance and virtually constant performance monitoring of all GPS satellites. The Department of Defense monitoring stations track all GPS signals for using in controlling the satellites and predicting their orbits. So, it plays a major role in the GPS system by and large, and hence this is a very critical element in the whole process of GPS. Along with the other informations, meteorological data are also collected by the monitoring stations, thus allowing for a accurate evaluation of the tropospheric delays of the GPS signals. The satellite tracking data from the monitoring stations are transmitted to the master control station for processing. This processing involves the computation of satellite ephemeris and satellite clock corrections. The next element is the space segment. The space segment consists of the constellation of Navstar Earth orbiting satellites. Currently, the Department of Defense plan calls for full constellation of 24 Block 2 satellites, out of which 21 are operational and 3 are in standby mode. Out of this 21 satellites which are there, these satellites are placed in 6 orbital planes which are inclined 55 degrees to the equator. The slide beside shows us the approximate location of each of the orbital planes and the satellites as they are revolving around the Earth's surface. These orbits are at an altitude of about 12,000 miles each, with orbital periods of 24 sidereal hours, that is a time which is based on star computations and is required for precise matching with the Earth's orbit cycle system. However, it may be noted that this is approximately half the Earth's period, that is 24 hours. The next block of satellites, known as Block 2R, these satellites are expected to provide improved reliability and better capability to the range between the satellites in order to increase the orbital accuracy. Each satellite consists of 4 precise atomic clocks, that is rubidium and cesium standards, and has a microprocessor on board for limited self-monitoring and data processing. The satellites are also equipped with thrusters which can be used to maintain or modify their orbits. Then we come to the next segment, which is the user segment, wherein the observations are to be taken by the user themselves. Well, this will consist of both the civilian and military users. At this point, it may be noted that military users require much more confidential targeting of points, and thus they are categorized separately from the civilian users, and GPS, as a matter of fact, provides a well defined segmented information data collecting procedures for both the type of user community. Well, it consists of all the earth based GPS receivers that have been designed, which can vary greatly in size and complexity, even though the basic design is rather very simple. The next slide shows a view of the GPS receiver which is there. We can see that a typical GPS receiver is composed of an antenna and a preamplifier, radio signal based microprocessor controlled and display device, data recording unit and power supply. The GPS receiver decodes the timing signals from the visible satellites, generally 4 or more, and after having calculated the distance from each satellite, computes its own latitude, longitude, elevation and time. This is a continuous procedure and generally the position is updated on a second to second basis. This is then sent to the receiver display device, and if the receiver has provisions for data capture capabilities, then it is stored by the receiver's data logging unit. Having had a look at the basic components of the GPS, now let us look at the procedure as to how do we really make the measurements, and this is what we call it as satellite ranging. GPS positions are based on the measurement of the distance from the satellite to the GPS receiver on the earth. The GPS receiver can determine the distance to each of the satellites. The basic idea of determination of position is that of resection or trilateration, which many of the surveyors use in their daily work. If the distance of the 3 points relative to the unknown point is known, then the positions of the unknown point relative to these 3 points can be determined. This is the basic principle of resection or trilateration, which is very commonly used in surveying. Similarly, if the distance of one satellite is known, then the position of the receiver must be at some point on the surface of an imaginary sphere of radius equal to that distance with origin at the satellite. By intersecting three imaginary spheres, the receiver position can be determined accurately. The GPS receiver also calculates the distance from the receiver to the satellite using the basic equation, that is, distance is equal to velocity multiplied by time, where velocity is the velocity of the radio signal, that is 290,000 kilometers per second, which is the speed of the light, and time is nothing the time taken by the radio signal to travel from the satellite to the receiver. All GPS satellites communicates all the information to the receivers by using codes. It broadcasts two carrier waves which are modulated by the coded information signal. The two GPS carrier waves are radio waves called L1 and L2 in the L band, that is 390 megahertz to 1550 megahertz. These are derived from the fundamental frequency of 10.23 megahertz generated by a very precise atomic clock. These radio waves travel at the speed of light. These high frequency transmissions from the satellite travel in straight lines and have very low power. It has been observed that the power of transmission from the satellite is about 50 watts. Hence, it is essential that the antenna of the GPS receiver have a direct view of the satellite itself. When we look at the signals which are being broadcasted by the satellite, first carrier wave L1, it broadcasts at a frequency of 1575.42 megahertz, which is 154 times the fundamental frequency of 10.23 megahertz, which has been generated by a very precise atomic clock. The second carrier wave, that is L2, it broadcasts at 1227.67 megahertz, which is 120 times the fundamental frequency of 10.23 megahertz. Further, to make these two carrier waves more effective and non-intersecting, these waves are also modulated by two codes. The L1 carrier has two codes modulated upon it. The first one is the course/acquisition code, or what we call it as CA code, modulated at 1.023 megahertz, and the second code is the precision code, or known as the P code, at 10.23 megahertz. This L2 carrier has only one code modulated upon it, that is the P code, that is at 10.23 megahertz. Along with this, the satellite also broadcasts a navigation message. That is, the information that the satellite transmits to a receiver, what it will consist of. First, the satellite's orbital and clock information. The second is the general system status messages, and the third is the ionospheric delay model. Well, these three informations are required after the observations have been made in order to find out the exact location of the point on the Earth's surface. And these three things have been already discussed when we were discussing the 5 logical steps. So, the navigation message is going to provide us all these information for the computation. The navigation code has a low frequency of 50 megahertz and it is modulated upon both L1 and L2 carrier waves. This is required so that if a user is only using one of the carrier waves, he will not be deprived of the navigation message. It communicates the data in a message, what we call it as GPS message or navigation message, as we have discussed just now. In order to distinguish the two waves that we have, that is L1 and L2 carrier waves, GPS receivers use different codes to distinguish between the satellites. It is very necessary because if the signals are being transmitted by the satellites are of the same information or content, then there would be a confusion at the observation level and also at the computation level. So, what we do is we resort to pseudo range measurements. For pseudo range measurements, we need to have GPS codes which are there. GPS codes are primarily binary in nature, and when we look at these GPS codes, there are 3 basic codes in GPS which are sent by the satellites: the precise code or the P code, the course/acquisition code or CA code, and the navigation code. The modulated CA code and the P code are referred to as pseudo random noise, or what we call it as PRN code. This PRN code is actually a sequence of very precise time which transmits the ground receivers to compare and compute the time of transmission between the satellite and the ground station. From this transmission time, the range to the satellite can be derived and is the basis behind the GPS range measurements. The CA code pulse intervals are approximately 300 meter in range, and the more accurate P code intervals have a range of 30 meters. Well, let us look at the importance of PRN code. The PRN code is a complex pattern, thus ensuring that the receiver does not accidentally synchronize with some other signals, so that there is no corruption in the data computations subsequently. The patterns are so complex that it is highly unlikely that a stray signal will have exactly the same shape. This is a very unique feature which has been adopted in GPS, so that there is a distinct characteristic between the signals which is being received from each of the satellites which are communicating with the GPS receiver on the Earth's surface. In order to do so, each satellite has been provided with a unique PRN code which ensures that the receiver will not accidentally pick up a signal from any other satellite. Hence, all the satellites can use the same frequency without signal jamming. Well, this also provides another advantage, and that is that the system cannot be tampered by any hostile force which may try to jam the system. In fact, the PRN code gives the Department of Defense a complete control to the excess of the GPS system. Also, these codes make it possible to use the information theory to amplify the GPS signals. Further, the complexity of the PRN code makes the whole process of GPS economical, and that is why GPS receivers do not require big satellite dishes to receive the GPS signals. Now coming to the pseudo range. It is a measure of the apparent signal propagation time from the GPS satellite to the GPS receiver antenna scaled into distance by speed of light. The apparent propagation time is the difference between the time of the signal reception and the time of emission. Hence, pseudo range is the time delay between the satellite clock and the receiver clock as determined from CA code or P code pulses. If a satellite is directly over the head of an observer, the travel time for a signal would be about 0.06 seconds, which is a very small time. Well, this time difference gives range measurements, but it is called a pseudo range since at the time of the measurement the receiver clock is not synchronized to the satellite clock. In most cases, an absolute three-dimensional real-time navigation position can be obtained by observing at least 4 simultaneous pseudo ranges. These pseudo ranges differ from the actual range due to the influence of satellite orbital errors, user clock errors, and ionospheric delays. With this knowledge regarding the GPS system, the user is now ready to take the observations. So, in the next session, I shall discuss the various GPS positioning methods. Thank you.
Thank you.